Tonight, we're watching something brutal and beautiful. How stars don't just make planets. They sometimes throw them away into deep space. When stars play cosmic billiards. Imagine a newborn star. Around it, a swirling disk of gas and dust, bright, hot, churning. Over millions of years, that disk condenses into planets, moons, comets, and asteroids. We like to picture that process as graceful. Tiny grains bump, stick, grow, and settle into neat orbits. But the truth is rougher. Planet formation is a violent game of gravitational billiards. Worlds collide, orbits cross, and some unlucky objects aren't just smashed. They're thrown out entirely, flung into interstellar space with enough speed to escape their star forever. When a star forms a planetary system, it is also, inevitably, building a population of exiles. From dust to worlds and to exiles. In a young planetary system, the basic ingredients are planetesimals, kilometer-scale building blocks, and planetary embryos, Moon to Mars-sized bodies. They orbit the star in a crowded, chaotic disk. Through collisions and mergers, some grow into full-sized planets, others are shattered into fragments or kicked onto wild orbits. Key steps: disk stage, gas plus dust in a flattened rotating disk. Planetesimal stage, dust clumps into rocks, rocks into mountain-sized bodies. Embryo stage, repeated collisions build objects hundreds to thousands of kilometers wide. Final clearing, gravity of the new planet sweeps the disk, either accreting or ejecting leftovers. Every time a smaller body swings past a larger one, there's a gravitational exchange of energy. Most of the time, the smaller body's orbit just changes shape. But sometimes it gets a huge kick. Enough kicks and an object can go from a cozy orbit to an elongated path that barely hangs on, or straight into escape velocity. This is where things start leaving. The three-body trick, how gravity flings things out. To throw something out of a star system, you almost always need three bodies. 1, the star. 2, a massive planet. 3, a smaller object, a comet, asteroid, or low-mass planet. When the small object passes close to the giant planet, the three-body dance allows energy exchange. If the smaller object passes behind the planet, relative to the planet's motion, it can gain orbital energy and be flung outward. If it passes in front, it can lose energy and be sent inward. This is the same basic physics we use in gravitational slingshots for spacecraft. But in nature, it happens billions of times over a system's youth. Given enough close encounters, some objects spiral inward and crash into the star or inner planets. Many are parked in distant, elongated orbits. A fraction get kicked so hard that their speed exceeds the star's escape velocity, and they become interstellar objects, permanently unbound. Simulations of forming planetary systems show that this is not rare, it's normal. One recent N-body study finds that in some configurations, 40 to 80% of initially formed planets can be ejected through planet-planet scattering over hundreds of millions of years, leaving behind only a fraction as the final stable system. Giant planets as gravitational catapults. In our own solar system, the main bouncer at the door is Jupiter. As the giant planets formed and migrated, they scattered countless icy planetesimals outward. Saturn, Uranus, and Neptune would pass those bodies along like gravitational relay runners. But once an object reached Jupiter, its enormous gravity could sling it onto a long, looping orbit, or kick it so hard that it left the solar system entirely. In many dynamical models, including the famous Gliese model of early solar system instability, Jupiter ejects vast numbers of small bodies into interstellar space, while others are parked in distant reservoirs. So when you picture Jupiter, don't just think planet. Think gravitational machine that has spent billions of years throwing rocks into the dark. Born to leave, comets and the birth of the Oort cloud. Not every scattered object escapes immediately. Many are thrown onto huge, elongated orbits that go far from the star but remain just barely bound. Over time, passing stars and the galactic tide, the large-scale gravity of the Milky Way, can gently reshape those orbits into a roughly spherical cloud surrounding the system, an Oort cloud. For the solar system, the classical picture is icy bodies originally forming in the Jupiter-Saturn, Uranus-Neptune region are scattered outward by the giant planets. Some are thrown to tens of thousands of astronomical units, AU, forming a huge reservoir of long-period comets. Over billions of years, encounters with passing stars and the galactic gravitational field randomize their orbits, creating an almost isotropic cloud. Statistical studies suggest that only a fraction of initially scattered bodies remain. Many are eventually further perturbed and fully ejected into interstellar space. For example, some simulations show that more than 40 to 60% of initial comets can be lost from an Oort cloud over the age of a planetary system, mainly due to stellar encounters. Why ejection is common, not rare. Put all this together and a picture emerges. Planet formation naturally produces many more bodies than will survive in stable orbits. Giant planets are efficient at scattering and ejecting those leftovers. Outer comet clouds act as halfway houses, from which many objects are eventually lost due to passing stars and galactic tides. Far from being unusual, ejection is a built-in feature of star systems. Recent modeling even suggests that to explain the observed population of free-floating planets detected by microlensing, typical stars may form 5 to 10 planets each, with a large fraction ultimately kicked out. Interstellar comets, rocks turned into messengers. When smaller bodies, comets and asteroids are ejected, they become interstellar objects. Most of them will never come close to another star in a way we'd notice. But every now and then one does, and if we're lucky and watching, we see it flash through our own system. The first confirmed cases, like Oumuamua and 2I Borisov, are almost certainly part of this ejected population. Fragments from other planetary systems tossed out long ago and wandering until chance brought them into our telescope's field of view. When you look up and see a star, remember this. It may have formed 5, 10, or more planets. If you want to follow those exiles, the rogue planets, the interstellar rocks, and the hidden mechanics that fling them into space, subscribe to Discovering the Unknown.